Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are going to deal with the session number 90. In the last session we have discussed cells related basic theory, basic points were discussed like what is EMF, what is internal resistance, on what factors internal resistance depends, and finally we have concluded with several equations related to terminal potential. Terminal potential V is expressed as E minus IR. What was the last conclusion in the previous session? Terminal potential V is equal to E minus IR, and this equation is shuffled in different form into different forms. Like V is replaced with I into capital R, okay, and later we have written expression for internal resistance, and we have written expression for current. Like that, this equation is modified into several other forms. Okay, so this is where we have concluded in the last session. Let me continue with further discussion. There are few points I'd like to quote. Now, let us say there is a cell whose EMF is E, internal resistance is R, E comma R. Let the cell is connected in a circuit and it started undergoing discharge. Let the current flowing through the cell, let it be I, small I. Okay, so it's connected in the circuit. I'm not drawing the entire circuit, so this part of the circuit is taken here. Okay, so terminal potential expression in this case, how it is written, terminal potential V can be written as E minus IR. That's how we write, isn't it? This is the expression for E or terminal potential. And right now what is happening? The cell is undergoing discharge. There is a reason for stressing on this point. We have cells which can be recharged, isn't it? There are cells which can, once they undergo discharge, we cannot recharge them back. Okay, those are called as primary cells. So secondary cells, they can be recharged. Okay, now what is going on? Is it recharge? No, it's undergoing discharge. When discharge is taking place, conventional direction of current will be taken like this, and inside the cell current will flow from what in this direction, from low potential to high potential inside the cell. Okay, so this is the expression for terminal potential when discharge is taking place. And look at this equation. If you observe this equation here, this E can be written as V plus IR, isn't it? So if we try to identify the relation between E and V, this is what we'll get. But from this equation, it is obvious that E is greater than V. E is greater than V. So remember, children, when a cell is undergoing discharge, the EMF will be greater than terminal potential. Okay, this is a very important point. What if the cell is undergoing charging? Let me take one more cell here. Let its EMF is E and internal resistance is R. When the cell is undergoing charging, the direction of current will be like this. Okay, unlike in the previous case, here direction will be like this. Okay, so from negative terminal to positive terminal you will have. So if this is the situation, in this case, the terminal potentials, equation becomes E plus IR. Okay, so when the discharge is taken, in the last session we have come to know that terminal potential will be less than applied EMF, and we have discussed about last volts also. Last volts is equal to IR. Okay, but when charging is taking place, terminal potential equation will be different. Terminal potential is what? Potential across the electrodes of the battery, electrodes of the cell. So in case of charging, what V is written as E plus IR, and here what is taking place? Discharging of a cell, and here charging of a cell. So in case of charging of a cell, V is written as E plus IR, and obviously here, if you try to compare E with V, E can be written as V minus IR. Therefore, E is less than V. In the previous case, E is greater than V. So this is a condition when discharging of cell is taking place. EMF will be greater than terminal potential. When the charging of a cell is taking place, EMF will be less than terminal potential. Okay, so these are two important key points connected with this one. And to continue with the grouping of cells, I'd like to add one point here, one concept I would like to introduce at this point of time. It's electric power. Because in case of grouping of cells, in case of cells, we will be using electric power concept here and there sometimes. So let us have an idea about what electric power is. Okay, and after that we'll get back to grouping of cells. Actually, after the cells related fundamental part is completed, immediately we have to switch to what a grouping of cells. But anyways, we'll complete first electric power, and then we'll make use of this electric power concept to understand cells much better. Okay, so what is electric power? Electric power. See, power is what? Rate of doing work. Electric power in the sense rate of work done to maintain charge flow in the circuit. Definitely, if charge is moving inside the circuit, some work has to be done, isn't it? So rate of work done to maintain the flow of charge in the circuit is nothing but electric power. So in terms of, mathematically, it can be expressed as P is equal to work done by time. Rate of work done to maintain the charge inside the circuit. So this W can be replaced in terms of potential as V into Q. This is what we have an idea regarding work done and potential from electrostatics, isn't it? So VQ by T. So here this Q is the average charge transported in the circuit in a time T. So this Q by T can be replaced with what? Current. So remember children, power is written as V into I, where V is potential difference and I is current. Okay, so if you want, you can modify this further. For example, according to Ohm's law, what do we have? Since V is equal to, how it can be written? I into, it can be written as R. Whatever this R is, resistance, external resistance connected in the circuit. Okay, if this is a situation from, I can replace V with IR. If V is replaced with IR, what I will get? IR, P is equal to IR into I. So I square R. Further, this I can be replaced with what? From this equation, I can be written as V by R, and substitute back here, and you will have one more form of power. So if you replace I with V by R, V into V by R, V square by R. So like that, electric power can be expressed in different forms. Okay, so this data is a bit important. Okay, so let us try to make use of this data to understand the cells related concept a little bit much better. Okay, so let me erase this. So what we came to know regarding power, it can be written as V into I, or power it can be expressed as I square R, or it can also be expressed as V square by R. What this power is, this is what rate of work which is being done to maintain the charge flow inside the circuit. Okay, so this is what we call it as power dissipation. When current flows in the circuit, what happens? All of we know electric wires gets heated because of resistance offered by the wire. When the charge is flowing inside the wire, what happens? There will be frequent collisions with the atoms, so heat will be generated. And though there is a hindrance by the atomic sides of the conducting material, how come this charge is able to flow in the conductor? We are maintaining potential difference. That potential difference is doing work to push the charge ahead, isn't it? So here, whatever work is done here, that work dissipates in the form of heat energy, and whatever power expression you have written here, this can be called as power dissipation. Power dissipation. And power dissipation can be expressed in these three different forms. V into I, P is equal to I square R, P is equal to V square by R. Okay, so I'll talk about one theorem called maximum power transfer theorem. Maximum power transfer theorem. Let us see what that theorem is. Maximum power transfer theorem. See, I'll consider a circuit containing a cell and a resistor, external resistance capital R. Let EMF of this cell is E and internal resistance offered by the cell is R. Let a current I is flowing in the circuit. Okay. Now, how this I can be written? Total current in the circuit is written as total EMF is how much E, and total resistance offered by the circuit. What is the total resistance offered by the circuit here? The total resistance offered by the circuit is this capital R plus whatever internal resistance is offered by the cell. You have to add those two things. Okay, so R plus R. Okay, whatever terminal potential equation we have got, V is equal to E minus IR. From that equation also you can write this I is equal to what? Total EMF divided by total resistance offered by the circuit. Here total resistance offered by the circuit is what? Current is flowing along this path. How much is the resistance offered by this path? R plus, and here one small r is getting added. So R plus R is the total resistance offered by the circuit. Now let us let us try to consider this power dissipated in the circuit. It can be written as I square R. Earlier I gave you three forms. Power is equal to V into I, or power can be written as I square R, or power can also be written as V square by R. These are the three different forms of power dissipation. So I have taken this form. Now I am going to replace this I with E by R plus R. If you replace with E by R plus R, what you will get? E square into R by R plus R whole square, isn't it? So this is the expression for power dissipated in a circuit containing one resistance and a cell, E square R by R plus R whole square. So now I am interested in one particular key point here. Power dissipation is there, and as you could see in this equation, power dissipation is dependent on resistances, internal resistance and external resistance. For a given cell, it depends on external resistance and internal resistance. Okay, so if these two parameters like internal resistance and external resistance are changing, or actually for a given cell R will be constant anyways, this external resistance is something you can tune it. You can either increase, you can decrease, or you can maybe you can take this external resistance equal to internal resistance also. Like that you can change. This is in your control. Okay, so if you change capital R from this equation, it is obvious that power dissipation will change. Power dissipation will change. If you want, you can draw one graph also. Okay, let us draw a graph a bit, or right away we'll do it. Power I will take on the y-axis, and resistance I will take here. So from this equation, the profile of the graph will be something like this. After reaching certain maximum value, again it decreases. Okay, and we'll find out what is that maximum value. We'll find out. Okay, so what power is dependent on capital R. So now I would like to know for what value of capital R the power dissipation will be maximum. What I'm talking about? I'm talking about maximum power dissipation. So let us try to understand this. At what value of capital or maximum power dissipation is possible? See children, at maximum power dissipation, dP by dr equal to 0. This is a mathematical tool. Variation of P with respect to R becomes 0 when at a maximum power dissipation. All of you look at this graph. At this point, if you wanted to find out the slope, actually slope of this curve is expressed as dP by dr, isn't it? And at this point, if you wanted to find the slope, what you are going to do? You are going to draw a tangent, and that tangent is going to be a horizontal line. For a horizontal line, what is the slope? It's 0. So at a maximum power dissipation value, dP by dr will be 0. dP by dr will be 0, because in this graph dP by dr, with respect to this graph, dP by dr represents slope, and at maximum value of power, what is happening to that slope? Slope is becoming 0. So dP by dr can be taken as 0 at maximum power dissipation point. So I am going to differentiate this one, whatever P is here. So d by dr of E square R by R plus R whole square equal to 0. Okay, there is a tool in differentiation. Okay, if you are familiar with that, it's okay, fine. If you are not familiar with that, whatever conclusion I will be drawing, just stick to that conclusion. Okay, let me go with the differentiation. E square R plus R whole square into d by dr of R is 1 minus. So you will be taking denominator as it is, you have to write here, into d by dr of R. Now you have to differentiate this, and you have to keep it intact. You are not supposed to differentiate this one. So I will keep R as it is, and I will differentiate this one. If I differentiate, what I will get? 2 into R plus R. And again you have to differentiate this one. Again, if you differentiate this one, what you will get? 1. d by dr of small r is 0, d by dr of capital R is 1. That's what you have to write. Divided by R plus R whole square. Actually, R, whatever denominator term is there, you have to take square of that. Already square is there. So what you will have? 4. It must be equal to 0. So let me simplify this. E square, it goes to the RHS side and it becomes 0. R plus R whole power 4 into 0, 0. So finally what you are left with? R plus R whole square minus 2R into R plus R equal to 0. Therefore, r plus r whole square is equal to, I am taking this term towards RHS side, 2r of r plus r equal to 0, and r plus r gets cancelled. Therefore, r plus r is equal to 2r. Therefore, if you take this r towards RHS side, finally what you are left with, r equal to r, small r equal to capital R. Internal resistance is equal to external resistance. It means dp by dr equal to 0 is possible at small r equal to capital R. If external resistance is equal to internal resistance, then dp by dr will be 0. If dp by dr is 0, what does it indicate? It indicates maximum power transfer. Okay, maximum power dissipation. So now we came to know for what value of capital R, for what value of external resistance, the power dissipation will be maximum. For what value of power capital R, it will be maximum if r equal to small r. So I'll consider that, and I'll find out how much is that maximum power dissipation. What is power equation? P is equal to E square R by R plus R whole square. Now I am going to replace capital R with a small r. If capital R is replaced with a small r, what you will get? E square small r. Here I am going to replace with small r plus r, 2r whole square is 4r square. R gets cancelled, therefore P maximum is equal to E square by 4r. Okay, so maximum power dissipation value is how much? E square by 4r. And here, corresponding to this point, what is the value of P? Now we came to know what is that maximum value? E square by 4r. And here what? Capital R is equal to small r. So this is about power dissipation. I am going to make use of this point to deal with cells, to deal with certain key points related to cells. So that I have given you this information. All that you need to remember is power is expressed like this: P is equal to VI, P is equal to I square R, P is equal to V square by R. You know how this equation is obtained. And P maximum is expressed as E square by 4R. And P maximum is possible under what conditions? If external resistance that you have taken in the circuit, if it is equal to internal resistance. Okay. Now let us discuss about grouping of cells. Okay, grouping of cells. What kind of groupings are possible? Two kinds of combinations are possible. One is series combination, the other one is parallel combination. I will start with series combination. Series combination. Okay, I will take two cells like this. If negative terminal of one cell is connected to positive terminal of the other cell, then you say that both are in series combination, and I will connect one external resistance here. Let it be capital R. Let first cell's EMF is E1, second cell's first cell's internal resistance is R1, second cell's EMF is E2, and internal resistance is R2. So these are the parameters that I have defined. Now both the cells, since they are connected in series like this, like negative terminal connected to positive terminal, the current will be like this. Let the current in the circuit is I. Okay. So if I wanted to find out what is the effective EMF offered by these two cells, since both the cells are trying to maintain the current along the same direction, they are not opposing each other. This one is trying to maintain the current along this direction. This one is also trying to maintain the current along the same direction. So here the effective EMF or E equivalent value of EMF can be written as E1 plus E2. E1 plus E2. And what about the internal resistance effective value? Small r equivalent value. Even see here one cell is there. It means corresponding internal resistance you can imagine as something like one small resistor here, another small resistor here. Both are in series only. So effective internal resistance can be written as R1 plus R2. What is the total resistance offered by the circuit? R equivalent is equal to R1 plus R2 plus R. This is the resistance offered to the flow of this current I. This is the path followed by current I. And what is the total resistance? R, capital R plus R2 plus R1. So what is the total effective resistance of this circuit? This one. Therefore, this current I can be expressed as total EMF divided by total resistance. Total EMF is how much? E1 plus E2. And total equivalent resistance is how much? R1 plus R2 plus R. That's how you can write expression for I. Now let us discuss few points connected with this kind of grouping. What if this cell is connected in reverse direction? Connecting in reverse direction in the sense something like this. Here negative terminal of one cell is connected to positive terminal of the other cell. Now what I am going to do is I am going to connect a negative terminal of one cell with the negative terminal of another cell like this. This is the combination that we can think about. And I will take one external resistance here. Let its value is E1, internal resistance is R1, EMF for the second cell E2, internal resistance R2. Okay. I'll assume one condition, E1 is greater than E2. If that is the situation, the current driven by this cell will dominate. So the direction of current will be like this. If at all E2 is greater than E1, then the current direction will be in clockwise direction. Since E1 is greater than E2, the current direction will be in anti-clockwise direction. Okay. Now what is the effective EMF? Here try to understand this point, children. This battery is this cell is trying to maintain the current in this direction, and this cell is trying to maintain the current in the opposite direction, isn't it? It's like both are opposing each other, they are not supporting each other. So here in this case the equivalent value of EMF can be written like this. How? E equivalent is equal to E1 minus E2. If at all if E2 is greater than E1, you can write this as E2 minus E1. E2 minus E1. So E equivalent is E1 minus E2, and R equivalent, directly I am writing total resistance R1 plus R2 plus R. Whether they are connected in reverse direction or in the same direction, it doesn't matter, resistance will be same, R1 plus R2 plus capital R. So in this case, whatever current is there in the circuit I, that I can be expressed as E equivalent by R equivalent, which is equal to E equivalent is how much? E1 minus E2. R equivalent is R1 plus R2 plus R. Okay. And let me talk about one point here. When they are connected properly in series, both are connected in series like this, negative terminal connected to positive terminal of the other cell, terminal potential across the first cell can be expressed like this. V1 is equal to E1 minus I R1, small I, whatever current is flowing here, we have taken it as small I. So this is what expression for a terminal potential across the cell 1. Okay, because cell is undergoing discharge, so terminal potential is expressed as E1 minus IR1. We had a small discussion about this one. Corresponding to this one also, what is the terminal potential? V2 is equal to E2 minus IR2. Unlike in this case, here see, this cell is undergoing discharge, whereas this cell is undergoing charging, isn't it? Because direction of the current here, it is like from negative to positive in this direction, and here positive to negative. We have already seen what charging and discharging cases. Here this cell is undergoing discharge and this cell is undergoing charging. Since this cell is undergoing discharge, the terminal potential across the first one can be written as V1 is equal to E1 minus IR1. E1 is equal to IR1. And terminal potential across the second one, it is written as V2 is equal to E2 plus IR2. The plus sign is taken because it is undergoing charging. And here we have minus n because it is undergoing discharge. So that's how you can have a brief idea about a series combination of cells. What if cells are identical? Identical cells in the sense all the cells are having same internal resistance, same EMF, and they are connected in series like this. Like that, n number of cells are connected. All are identical. E comma R, E comma R, E comma R, and so on, E comma R. Like that, n cells are connected. In this case, what is equivalent EMF? E plus E plus E plus and so on, n E's. So you will have n E, and R equivalent effective internal resistance. N cells are there, so n R, R plus R plus R plus R plus R, like that. If at all if this is connected to what some external resistance capital R, in that case R equivalent will be, total resistance will be sum of internal resistance plus external resistance, NR plus R. And if you wanted to write expression for current in this case, when n identical cells are connected in series, how you can write? I is equal to E equivalent by R equivalent. E equivalent is NE, R equivalent is NR plus R. That's how you can write. Okay, and this I, whether it is maximum or minimum, it can be decided by this denominator. If at all, if r value is extremely large when compared to small r, what you can do, you can ignore this nr. If a small, if r value, external resistance value is very much smaller when compared to nr, you can ignore this one. Okay, then nn gets cancelled, you will have I as E by r. So like that you can make modifications. Now I am going to think about one more possibility. Here what? These two cells are connected in reverse direction. Okay. Here I am going to assume that n cells are there. Total how many cells are there? Let us say n cells are there. Among those n cells, few cells are connected in reverse direction. Few cells are connected in reverse direction. Look at this picture once. If these two are identical cells in the sense both are having same EMF, both are having same resistance, internal resistance, then what will be the equivalent EMF? It will be 0. It will be 0. If two cells are connected in reverse direction, if both are identical, then what happens? Effective EMF will be 0. It means if one cell is wrongly connected or connected in reverse direction, it kills another cell and two cells becomes inactive. Two cells becomes inactive. For example, if you take 5 cells, one cell is wrongly connected. What it is going to do? It is going to consume another cell and two cells becomes inactive. Their contribution by two cells among those 5 cells will be 0. If you are told to find out what is the effective EMF of that series combination, 3E will be the effective EMF. What I am talking about? I am taking 5 cells. 5 cells are taken in series combination, but one cell is wrongly connected. Wrongly connected in the sense like this. Negative terminal is connected to negative terminal. If that is the situation, what will be the effective EMF? For each wrongly connected cell, there will be another cell such that the sum of EMFs of those two cells becomes 0, isn't it? So among these 5 cells, if one cell is wrongly connected, it is going to consume another cell and two cells effective contribution to the EMF will be 0, and what is the effective EMF? Effective EMF will be contributed by rest of the 3 cells, 3E. Okay, so remember children, if 2 cells are wrongly connected, 4 cells becomes inactive. Inactive in the sense there won't be any contribution. If among some 10 cells are there, 3 cells are wrongly connected, then 3 plus 3, 6 cells will be inactive. They don't contribute anything to what effective EMF. So if n cells are considered, let n cells are in series, let m cells are wrongly connected. Wrongly connected in the sense like this, negative terminal connected to negative terminal, like that connected. Just now I told you, if one cell is wrongly connected, 2 cells becomes inactive. If m cells are wrongly connected, how many cells are going to be inactive in the circuit? 2m cells. How many cells? 2m cells. Therefore, number of cells which will be inactive in the sense they don't contribute anything to effective EMF will be inactive is equal to 2m. Therefore, number of cells which are active is equal to n minus 2m. Among n cells, now 2m cells have become inactive. Therefore, active number of cells will be n minus 2m. Therefore, now our entire theory repeats again. Equivalent EMF, E equivalent is equal to n minus 2m into E, if each cell is having EMF E. I have considered identical cells here. Okay, if you take cells with a different EMFs, situation will be a bit complicated. If you are having too many cells, it's a bit difficult to write everything here. Okay, so I have taken to simplify the situation, I have taken all are identical cells. I have taken all identical cells. Now, R equivalent. Remember children, whether they are wrongly connected or properly connected, it doesn't matter. Resistance will be offered by the entire path. So, total number of cells in the series combination is how many? Number of cells are there? N. So, what you will have? Total internal resistance. Internal resistance will be NR. Therefore, effective total resistance of the circuit NR plus capital R. This capital R is what? Something like this. N cells are there. Among those n cells, m cells are wrongly connected, and external resistance is there. External resistance capital R is there. So equivalent resistance is NR plus R. Therefore, current through the circuit is E equivalent by R equivalent. E equivalent is n minus 2m into E, and R equivalent is NR plus R. So that's how you can write the expression for current. Okay, so these are a few details about series combination. In the further sessions, we'll try to discuss about parallel combination, and we'll try to explore few other points connected with the cells. Thank you, students.